So alternating series, go plus minus, plus minus, plus minus, plus minus. Let's look at this here. So the notation we'll use is these b sub n's are positive, and so we get b1 minus b2 plus b3, da 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 da. It's not important. It's not important that the series starts with a plus. That's just our nomenclature. It could have minus plus, minus plus, minus plus. That would be fine. So here's the main theorem. Given an alternating series, if we can prove that b sub n plus 1 is less than b sub n, which is to say that the sequence of terms forming the series, the positive, if you like, the absolute value of the terms. But anyway, these have to be decreasing for all n, and the limit of the b sub n has to be 0. If we have those two things, then we can conclude that the series, alternating series, converges. All right. So let's look at an example. Well, okay, well, a little bit more first to comment. On the other hand, if the b sub n does not go to 0, then this diverges by the nth term test, because then a sub n would be minus 1 to the n minus 1 times b sub n, which of course is not going to go to 0 as n goes to infinity, so by the nth term test, that would be a divergent series. All right. Now, here we go. So let's look at the so-called alternating harmonic series. It's like the p equals 1 series, but now with plus minuses. So our b sub n is 1 over n, right? And clearly 1 over n decreases, it has limit 0, so the alternating series test applies. And we get that this series S converges by the alternating series test, which you can abbreviate as AST, right? I'm sure I'll start doing that soon. And this one's kind of neat because you can actually picture it, all right? So if we picture the alternating harmonic series, I can picture partial sums. So like the nth partial sum would be sum k equals 1 to n, minus 1 to the k minus 1 over k, right, which is this. So of course, when we put in 1, we just get 1. The second partial sum is going to be 1 minus a half, plus a third, minus a fourth, plus a fifth, minus a sixth, plus a seventh, minus an eighth, plus a ninth, minus a tenth, and so forth and so on and so on and so on. And so, as you can see, it's kind of like bouncing. Anyway, eventually it homes into the value to which it converges. As n goes to infinity, the nth partial sum converges to something in here, and if you tilt your head and squint, you can see that that's natural log of 2. Okay, that's a joke. You can't really see that from my picture, but we'll prove through a somewhat circuitous argument later that this actually converges to the natural log of 2. What it converges to doesn't really matter too much to our purpose here. We're really just interested in the question of, does this series converge or diverge at the moment? And then a little bit later we'll come back to that question of estimating the series. Turns out for alternating series we have a really beautiful estimation theorem. Oh look, what do you know? That's up next. So the alternating series estimation theorem, or ASET, says the following. It says if you have a convergent alternating series, like so, then you want to estimate the series with the nth partial sum. Then if you take the full series minus the nth partial sum, that has error. This is the error, the difference between the full series and the nth partial sum of this alternating series. It's less than or equal to the n plus 1th term. So what this is saying is if I use the first 5 terms in an alternating series, it's within the 6th term of the answer. Again, assuming we're working with a convergent alternating series, of course, but that is really, really simple, much easier than the rule we had before for the integral test, which actually required integration. So, in words, the error in the nth partial sum is at most the b sub n plus 1, or in other words, the next term in the series. So here's a good example. Suppose you wanted to calculate the alternating harmonic series within 0.01 of its exact value. So that means that you want 1 over n to be approximately 0.001. Maybe we'll take a little bit more just to make sure we got it. So I want to, if I could solve that equals to that, I'd be in business. So that, n equals 100. So the 100th partial sum should have an error of at most 1 over 101. 1 over 101 is a little bit smaller than 0.01, so that should do it for us. And I will let technology help here. All right. So the 100th partial sum, and I'm probably used Wolfram alpha here. All right. In fact, Wolfram alpha will calculate stuff like this. You just say sum 1 over n from n equals 1 to 100. Well, I mean, I'm sorry, not 1 over n, but minus 1 to the n minus 1 over 1 over n. And it'll do stuff like this pretty reliably. But anyway, 0.6882 is the answer. And for what it's worth, the natural log of 2 is about 0.6931. And the difference between log 2 and the 100th partial sum is actually 0.005, which as advertised it's less than 1 over 101. 1 over 101, oh, I have not calculated, and I don't have a calculator handy, so it'll have to remain a mystery at the moment. Example 3, moving along here, we have the alternating p equals 2 series. So we have bn is 1 over n squared, 1 over n plus 1 squared is less than 1 over n squared. So it's a decreasing sequence. The terms we're summing, ignoring the plus or minus. Of course, the limit as n goes to infinity of 1 over n squared is 0. Hence, this converges by the, not this, but S converges by the alternating series test. All right. All right. Furthermore, I didn't see I had more of my paper left here. If I wanted to approximate it, I could. All right. So the third partial sum, 1 minus the fourth plus the ninth, about 0.861. And the alternating series estimation test says that that is within 1/16 of the true answer, whatever that is. 0.0625, all right, is the error. So this means that if we approximate, if we say that we can say that the p equals 2 series is equals to 0.861 plus or minus 0.0625. That's what the alternating series estimation theorem gives us. Example 3, we have the sort of p equals half alternating series. Again, we can argue that we meet the conditions of the alternating series test, namely the b sub n's are decreasing, and they limit to 0, right? Okay. Here's another approximation example. Suppose we wanted to approximate this alternating series to 4 decimal places, 4 certain decimal places. All right, that means we want the error to be in the 5th decimal place. So that means we want an error of 0.0001 to be safe. I think you could get away with 0.0004, I think, technically, but I'll make it 0.1 just to be safe. So here the b sub n are 1 over 2n factorial, which you can check are positive and decreasing. And so we need that bn is less than 0.00001. So that if we can solve equality here, that would you know, that's what we need. And so there's this kind of problem. What you want to do is just start plugging in numbers and do some tinkering until you see where it happens for you. You can't. There's no nice way that we know that you can just take n factorial and like take the inverse function of it. As far as I know, there's no. I mean, I don't know. There may be some calculator out there somewhere, but the best way I know to do is just to plug in some numbers and see where it goes. So 1 factorial. So plug in 1, plug in 2, plug in 3, plug in 4, plug in 5. And I get, 0.5, 0.042, 1.39 times 10 to the minus third, and 2.48 times 10 to the minus fifth. Now this might actually be small enough, but just to be safe, I went one more. Then we get 1 over 10 factorial, which is actually 10 to the minus 7th. All right, so this actually would probably give us 6 decimals if we go to the 4th partial sum here. So there you have it. If we want to approximate minus 1 to the n over 2n factorial, excuse me, to, well, our original aim was 4 certain decimal places, but I think this is actually, if I kept more decimals, I would have 6 certain decimals. Oh well. What's that? Plus or minus 2.75 times 10 to the minus 7th is what the alternating series estimation test tells us here. It's kind of neat. And I would also point out to you that, you know, there's a great contrast here, right? When we looked at the previous example, we needed out to the 100th term to get the first 2 decimal places, right? Whereas this, to get to, in fact, the first 6 terms, we only had to take the first 4 terms in the series, right? So in other words, this series converges much faster than the alternating harmonic series. In fact, the alternating harmonic series is kind of a, you know, kind of a slowly converging thing. Just like the alternating, just the harmonic series is a slowly diverging thing as well. But anyway, so next up is examples of absolute convergent ratio and root tests, so we'll get to that next time.